We've shown some impressive tests when it comes to the wing of the DarkAero 1 prototype, but one thing missing from these tests was how the load going through the wing transfers into the fuselage. Like in an earlier video, I said the center section of the wing is one of the most heavily loaded structures in the entire aircraft. Now I said one of the most because really all of that load that you saw going through the wing had to also go through 4 attach lugs that extend off the fuselage. In the case of our wing, when it came to simulating flight loads, we could apply concrete bags across its entire area. But in the case of our fuselage, we had to take this same load and apply it to a much smaller space. Additionally, when you pull or push on these 4 lugs, you have to also pull or push back on the rest of the fuselage to keep it from moving. The fuselage structures are designed around specific flight loads. So the challenge for us became, how do you test these 4 lugs to the same loads that the wing saw without breaking the rest of the fuselage in the process? Let's talk about it. Let's start off by discussing what these lugs are for. The short answer is that they allow loads to be transferred from the wing to the fuselage while allowing the wing to be removable, but there's a bit more to it than that. The DarkAero 1 is a kit aircraft designed for speed, range, and efficiency, and it is delivered to builders as a set of parts that they assemble into the final aircraft. Structurally, bonding the wing permanently into the fuselage would be the simplest and strongest option from a design standpoint, but doing so forces builders into a much larger workspace because the plane takes up more space with the wing attached. Also, if you ever want to ground transport the DarkAero 1 in, say, a U-Haul, making the wing removable is somewhat of a requirement. With a removable wing, the question then becomes, how do you maintain the structure and the strength of the wing to fuselage interface? Many aircraft solve the problem of a removable wing by breaking the wing up into multiple segments. From a manufacturing standpoint, this can kind of make sense. It can mean easier handling and make the shipping of everything much simpler. The downside to this is that as you break the wing up into pieces, you have to add additional joints. These joints add weight, complexity, and additional potential failure points. If you can build the wing as a single structure, it's almost always lighter, stronger, and more aerodynamically clean compared to a multi-piece wing. So from that standpoint, a single-piece wing became our approach. And once we committed to this, we needed a structurally efficient way to transfer the loads from the wing and into the fuselage, which led to the solution of having these 4 wing attach lugs. These lugs are CNC machined from a carbon fiber plate stock and then bonded into the fuselage. One thing to point out here is that they are tightly integrated with the armrests, so this meant that we couldn't just do a simple bench test comparing it to, say, the strength of a lap joint. The structure is a little more complicated than that, which inherently meant we had to test it similar to how we tested the wing structure. Another point I want to make is that these tests that we're performing, whether it be the wing or the lugs, are structural tests, and as such we would do these on the ground and not in flight. The consequence of a structural test can mean a structural failure, which you would not want to find out when human lives are at stake. The goal of these structural tests is twofold. Number one, we want to simulate a target load on the thing being tested, in this case the wing lug. And number two, we want to do this in such a way that we don't damage any surrounding structure that we are not actually testing. In the case of the wing, when we're testing it, the wing test stand is what's being reacted against, and the forces that are being counteracted as we apply load to the wing are going through that test stand and into the ground. In the case of the wing lugs, we couldn't do this necessarily because they are bonded into the fuselage. So if we pull or push on them, we have to constrain the fuselage to prevent the whole fuselage from moving. And so that meant that the same loads that are going through the lugs are in a way also going through the fuselage. Another example that kind of hints at this from aviation is in the case of the Voyager aircraft, where the team had built such a highly optimized aircraft that they actually couldn't structurally validate the thing without potentially breaking the rest of the airframe.
It was not possible for me to test the Voyager structure before it flew. The Voyager's fuselage is so weak that if you just go up to it and knock on its skin, you've damaged its structure and failed it. So I knew right off the bat I would not be able to even do a 1G static load test of this airplane.
Another interesting way that we could have gone about this problem of testing the wing, the lugs, or both would be to consolidate this into a single test where we would attach the wing to the fuselage and then test the entire assembly all at once. The reason we didn't do this was that we didn't want to have a cascading failure that would take both down in the process. So it was much easier for us to split this risk up into a wing lug test and then a wing test, and then overbuild the stands in each of those cases so that we could focus specifically on the aspects that we were testing. But I'll hand it off to Ryan, who went into more detail about what went into the process of developing the test stand for the wing lugs.
We have the lug load test still set up. Currently it's in the negative lift load configuration, so we can go through some of the key features of it. First off, you'll see that there is a 80-20 frame mounted into the cockpit area. This is mounted to the same 4 lugs that the wing will mount to, using the same exact bolt holes. And there's also an 80/20 frame down below the aircraft, and there's 2 turnbuckles spanning between these 2 frames. The 80/20 framing spans in the longitudinal direction of the aircraft, and what this does is it allows us to move the turnbuckles forward and aft in relation to the wing mount lugs themselves. And so then as we're applying the different loads or tensioning the turnbuckles, then we can simulate different aerodynamic moments that the wing may be generating, or control surface deflections, and even asymmetric loading cases if we tighten the tension on one turnbuckle more than the other. Each turnbuckle is hooked up to its own load cell, and the readout from that load cell is what tells us how much load we're putting into the lugs. This is a static load test, and so we could have used sandbags just like we did with the wing, but just the sheer volume of sand or concrete that we would have had to use to impart the same amount of load on the lugs as we did the wing would have gotten out of hand. So instead of using sandbags, we used turnbuckles. The turnbuckles can be tightened pretty easily just with a crescent wrench, and then if any failure were to occur, the turnbuckle is not going to release a lot of kinetic energy, meaning as soon as the distance between the 2 ends of the turnbuckle shortens from a failure, all energy would safely leave the system. Using turnbuckles is a similar test methodology as a wiffle tree. For this situation, we are carrying about the loads both laterally and longitudinally, so it's kind of a 2-dimensional wiffle tree in that respect. And then we are reacting that load against the fuselage itself in this forward region and the aft region. That's what the support is here. A couple cinder blocks stacked up. We could have made this a metal frame or some sort of 80/20 frame, but the cinder blocks were quicker for just getting this test off in a timely manner. The aircraft is ultimately resting on foam, and that foam is machined to the contour or outer mold line of the aircraft so that we are evenly dispersing loads across large regions of the aircraft skins. If we had to load the lugs up to load so high that it's not easily achievable with a turnbuckle, we would have to move to hydraulic cylinders, and that's what you'll see in larger structural tests like a rocket stage. Another thing to point out about this test setup are the pieces right here. So these are machined out of aluminum. I've been calling them the wing root rib simulators. So what this does is it simulates the same moment arm as the wing root ribs, so the part of the wing that interfaces directly with the lug that has the corresponding bolt hole. So this interfaces with the lug itself on the test and then replicates the wing root geometry, both in height and then angle of this top profile. And then what we've done is we've machined in the root rib deflection angles that we measured during the wing test. So as it's mounted here, this is forcing the lugs that are attached to the fuselage, it's forcing the lugs either out or in as the wing deforms under load. We machined a couple of these wing root rib simulators so that we have an angle representative of negative lift loads, positive lift loads, and then also just no root rib angular deflection straight up and down as a true 90-degree, sort of a proving out the concept of the test stand. We also have the carbon test wing section installed. So as we are pulling on the lugs, either up or down, we are kind of bending the fuselage. The test wing section helps react some of those loads. Here we have a ratchet strap that's hooked up to another load cell, and what this is doing is allowing us to impart drag loads onto the lugs. This is fixed to the 80/20 frame, which is then fixed to the lugs, and as you produce lift, you also produce drag. We are imparting lift loads onto the lugs with the turnbuckles, and we're imparting drag loads onto the lugs via ratchet straps and a subsequent load cell on each side of the aircraft. For the positive lift load rig, it was essentially the same thing, but this 80/20 frame, instead of being below the aircraft, was resting on top of the aircraft, and then it was once again bridging between the forward portion and the aft portion to react to loads. Overall, this test setup worked out well. It was efficient to set up. It allowed us to impart the loads on the lugs in a very controlled and safe manner, and it didn't hurt or damage any neighboring regions of the aircraft.
As Ryan was saying, there were a number of tests we did on the wing lugs to validate them for flight testing, and we're happy to report that the lugs got through all these tests without any issues and without damaging the rest of the airframe in the process. Speaking of flight testing, we've had a number of people reach out to us and ask about our overall progress towards first flights, and we just want to take this opportunity to mention that we have a milestone section added to our aircraft page, which serves as a roadmap towards this goal. You'll also notice that these milestones go beyond just the goal of first flights, and we did this to recognize not just the challenge of getting the prototype to fly, but also the overall challenge of getting our company to a point where we can sustainably build kits and ship them for customers. We're able to do all of this without external investment by designing, manufacturing, testing other airframes in the background through our services work. All this work has played an important role in allowing us to build the team towards the long-term ambitions of the company. If you'd like to join the team, check out the careers page at the link below and apply today. With the wing lugs now validated, we're moving on to the next set of milestones towards first flight by conducting the remaining airframe validation tasks, but we'll save that for a future video. Thank you all for watching. We'll catch you next time.